Okay, so far we are done with chapter 1, which is the mathematical modeling of physical system, mathematical modeling of control system. Now that we have the model, okay, before that, what is mathematical model anyway? Mathematical model is just the relationship between input variable and output variable in terms of equation. Now you have a precise relationship between input and output. So today, the natural progression from there is we want to analyze how the output will behave, how the output will respond to a certain type of input variable. So that is what we call a time response. So in mathematical terms, that we want to obtain the solution to the mathematical model. Or in control engineering, we use this term time response. So what is time response? Time response is a study of how the output variable. Okay, I'll let you settle down first. Okay, just make sure that you have switched off your microphone. Okay, so every time you join us, please make sure that your microphone is switched off so that we don't hear any background noise. Okay, so in terms of mathematics term, we want to obtain the solution to the mathematical model, how the output responds to the input signal. Normally in control engineering, we call that time response. So time response of a control system is a study on how the output variable changes with a typical input signal. So when the system is subjected to some form of input signal, we want to know how the output is going to behave. So these are some examples of input signal. Let's say we put a step input signal. For example, let's say you have an oven. Imagine that the input is the electrical voltage, and then the output is the temperature in the oven. Let's say you give a sudden value of electrical voltage. So that is called a step input. So how does the system is going to behave? How does the temperature will respond with respect to time? So that is what we mean by time response in control engineering. How the output signal responds to a certain type of input signal. So the input signal can be a step input, can be an impulse input, can be sinusoidal, can be ramp input. So for different type of input, of course, we are expecting to get a different type of response. So today we are going to learn how can we obtain the solution to our mathematical model when the system is subjected to a certain type of input. For those of you who do not pay attention when you took engineering mathematics, I don't know, engineering mathematics 1 or engineering mathematics 2, probably today you're going to wish that you have paid attention in your math class, because if you do, then this is just will be a revision of your one of the topic in your engineering mathematics. I'm not just going. I didn't do that just to scare you, but I imagine that this is just a review to what you have learned in engineering mathematics. So, okay, now imagine that the system is subjected to one of these input, and then we are going to have we are going to observe the output. In general, the output is going to behave something like this. It's going to take some time before it reaches the final solution. So we call that this is the transient. So this is the output versus time. Output versus time. So this is what we mean by time response. We are going to observe the output variable with respect to time. So when the system is subjected to a certain input signal, so the output is going to respond. So the response is going to is divided into two parts. it's going to take some time before it reaches a final value. So this is called the transient state. When it has reached the final value, we say that it is in a steady state response. This is in general. So we are going to look into details, specifically how the response is going to look like. Sometimes there's no oscillation, sometimes there is no overshoot, sometimes the response is very fast, sometimes the response is very slow. So we are going to analyze that here in this time response in this time response chapter. All right, so in general, our mathematical model is either in the form of differential equation. See, it's either in the form of differential equation, sometimes second order, sometimes third order, it can be as high as nth order. So in general, it's going to look something like this in a differential equation, or it can also be in the form of transfer function, where you already take the Laplace transform of it. So either way, we want the solution to this differential equation. Sometimes you have initial conditions, sometimes you don't. So for example, here, this is we have been looking at this example for several times now. So when you get the mathematical model of this example, it's going to be a second order differential equation. Okay, so let's go back to my notes here. So if you derive the transfer function, if you derive the mathematical model of this translational mechanical system, you're going to get something like this. Okay, so this is a second order differential equation with constant coefficient, and then depending on what type of input, then you're going to have a different response. So here we can imagine that. Okay, now imagine that we are going to we give certain input here. So this is the input variable, which is xi. This is output variable xo. Imagine now you give a step input. Let's say you move the displacement on the left hand side of the spring here. Let's say you move this by 1 meter, immediately 1 meter. So the response is not going to immediately reach 1 meter. So it's going to take time. Sometimes there's oscillation, sometimes you're going to move very slow, sometimes you're going to have overshoot. So depending on the parameters here, you are going to get different kind of response. So here, depending on the input signal here. But anyway, in general, you are going to get the mathematical model will be in the form of differential equation. So in this case, we have this second order differential equation. So how do you solve this differential equation? If you had paid attention in your engineering mathematics class, you already know how to solve this. There are several ways that you can solve this. Linear differential equation with constant coefficient and whatever. One of the easiest way to solve, it's not one of the easiest, one of the straightforward way to solve this differential equation is to use the Laplace transformation. Normally, control engineers prefer Laplace transformation because we already have the transfer function. So we are going to solve the differential equation using Laplace transformation. I'm not here to teach you what is a Laplace transformation, how do you get Laplace transformation. You have learned that in your engineering mathematics class. But in general, you can transform a time domain function, f of t. So the small f normally denote the function in time domain. You can transform that, you can take the Laplace transform of any time domain function into a Laplace domain. Laplace domain, normally we represent that by a capital letter, f of s, by taking the integral e to the power of st multiplied by the function dt. So this is the definition of Laplace transformation. The visualization of this, what do you get out of it? I'm not going to teach you math here. We are just going to use Laplace transformation to solve a differential equation. That's all. Okay? The visualization of Laplace transform should have been explained by your engineering math lecturer. But just for the sake of completeness, I'm going to use the definition of Laplace transform to make a transformation of the easiest form of f of t. So the easiest function is, of course, f of t is just equal to 1. So this is the easiest one. Here. What is the Laplace transformation of f of t is equal to 1? This is the simplest function there. I always like to solve simple functions, simple problem. I've told you many times already. Difficult problem, of course, that's your job to solve difficult problem. Okay, so imagine now we have f of t is just equal to 1. Then we are going to get the Laplace transform of that. This is very simple and straightforward. Okay, just use the definition of Laplace transform. Okay, so this is our f of t. F of t is just equal to 1. So this is the definition of Laplace transform. So the Laplace transformation f of t is just the integral from 0 to infinity e raised to the power of negative st and multiplied by the function f of t. But our function is f of t is just equal to 1. So that will reduce just this integral. And of course, you can just go ahead and evaluate that integral, and you get 1 of s. Finally, you get, after you evaluate the integral between the limit of 0 to infinity, so you get 1 over s. So this is if f of t is equal to 1, in time domain equal to 1. So in Laplace domain, the capital F of s is equal to 1 over s. That is the idea of Laplace transformation. We're not going to do this every single time we have a function f of t. We are just going to use the Laplace transformation table to help us solve the differential equation. So we're just going to go ahead to the Laplace transformation table. There, okay, there's your Laplace transformation table. So this is the pair of time domain f of t. Small f of t is in time domain. Capital F of s is in Laplace domain. So you have a pair here. You have an impulse, then you are in time domain, so you have 1. A unit step is f of t is equal to 1. In Laplace transformation, you get 1 of s, and so on and so on. A polynomial, exponent there, sine wave. We have this a pair of time domain and Laplace domain element here. And so we are going to use this. So I'm going to attract your attention to this Laplace transformation of the first derivative. This is dy dt. dy dt, if you have dy dt, of course, in our mathematical model, we have differential equation. So when you want to take the Laplace transform of the first derivative, it is just as capital Y of s minus y of 0. So y of 0 here is the initial condition in time domain. This is y of 0, y at t equals 0. Please distinguish between capital Y and small y. Small y represent time domain value. Capital Y represent the Laplace domain, the frequency domain. Sometimes people say that as well. So this is the initial condition. Y of 0 is the value of y when time equals 0. Again, if you have a second derivative here, so this is y double prime. Y double prime is the second derivative of y with respect to time. So when you take the Laplace transform of a second derivative, you get s squared capital Y of s minus sy of 0 minus y prime of 0. I'm going to attract your attention here. So y of 0 and y prime of 0 are the initial condition in time domain. The value of y at time t equals 0, the value of y prime at time t equals 0. So you can move back and forth. When you take the Laplace transform, you get the expression in the right column. When you take the inverse Laplace, you get the expression in time domain in the left column. So we are going to use, again, this is not a complete This is not a complete Laplace transformation table. If you want a more complete set of Laplace transformation table, you can always go to your calculus textbook or any mathematics textbook. Then you can get this a complete Laplace transformation table. Now I think you wish that you have paid attention more and more in your mathematics class. Okay, so let us solve an example using this Laplace transformation technique. Okay, so now, we have this simple translation of mechanical system. So find the time response xo of t for a unit step with the initial state. So this is the initial value xo equals 0. So initially xo here is equal to 0. So you give this 1 unit step. Let's say you move this the left hand side of the spring by 1 meter, and then we want to observe what's going to happen in what is going to happen on the for the piston inside the cylinder. So the first step is, of course, to obtain the differential equation and then solve this using Laplace transformation technique. Okay, so we are going to assume that the mass of the piston there is equal to 0. Then we can get the mathematical model. Okay, there. So this is the piston there. So you're going to have force in the spring and the damping force. We assume that the mass is equal to 0. So the summation of forces equal mass times acceleration. Since mass is we assume to be equal to 0, so we have just the spring force minus the damping force is equal to 0. So there's no term mass times acceleration here. We assume that the mass is equal to 0. And then now we can rearrange the differential equation in terms of output variable on the left and input variable on the right. Now, in the question, we were given that k is equal to 1, c is equal to 1. This is for simplicity. The parameters k is equal to 1, the parameter c is equal to 1. That is just for simplicity. Substitute that into our model. For k equal to 1 and c equal to 1, so our differential equation is now simplified to just first order differential equation in terms of xo, and then we have this input variable xi. And then we take the Laplace transformation of that. Imagine now, when we take the Laplace transformation, the initial conditions are 0. It is given by in the question. So the initial condition is 0, so you don't need to take you don't need to worry about the initial condition. But most of the time the initial conditions are 0, but you need to be careful. Sometimes the initial conditions are not 0. All right. So take the Laplace transform. This is the first derivative. Since the initial conditions is 0, you get just as xo of s. Take the Laplace transform of x0, you just get a variable in Laplace domain. Again, this is the input in Laplace domain. But since we have the unit step input, this is also defined in the question. See, this is a unit step input. For a unit step input, when you take the Laplace transform of that, you get 1 over s. Okay. This is a unit step input, 1 over s. 1 over s is a unit step input. So this is the Laplace transformation of the first derivative. So this is just the Laplace transform of the variable. And then you can solve, after you have taken the Laplace transformation, and then you can solve for the output variable in terms of Laplace domain. You get 1 divided by s divided by s plus 1. And then to get the solution for this, you need to take the inverse Laplace transformation of that. But if you look in the table, there is no element in the table that correspond to this form of fraction. There's a simple 1 over s, negative 1, s plus 1. If you look back into the table, Okay, so you have this 1 over s. You can take the inverse Laplace off. And then you have this 1 divided by s plus alpha here. So there is no elements that directly correspond to that fraction. No. So you need to perform partial fraction. You need to perform partial fraction so that the elements are equivalent to the elements in the table. Once you have performed the partial fraction, and then you can take the inverse Laplace of that. The inverse Laplace of 1 over s is just 1. We have proved that in our first example today. The inverse Laplace of that is just -1 e raised to the power of -1t. The inverse Laplace transform of this. Again, make the table friendly, that 1 divided by 1 plus alpha, the inverse Laplace of that e raised to the power of -alpha t. All right, so now here we have this solution. So this is the solution of the problem in time domain. The output variable. This is what we want to analyze. How the output variable behave when the input variable is a unit step. It is 1 minus e raised to the power of -t. You can plot that. This is just an exponential function. So this is the transient part. It's going to take some time before it reaches final value. This is called the transient part, and this is the steady state part. You can imagine that. Go back to our original problem. Okay, so when we move the left-hand side by 1 meter, finally the piston is going to move 1 meter, but it's going to take some time. It's going to slowly, because of the viscosity of the fluid in the cylinder. So the piston is going to take some time to reach its final value. The final value of the piston is also going to be 1 meter. Just look at the solution here. Okay. It's going to take some time, increase until it's equal to 1, and then this is it has reached its steady state. So that is what you have to go through when you want to solve a differential equation using Laplace transformation technique. Do you have any question? No question. All right, no question is good. Let's try another one, I guess. Okay, let's try another one. Where is this? Okay, this one. Okay, let's solve this problem. Example 1 again. See, the numbering of example is, you might get confused, but if you pair our notes with the note if you pair this note with my handwriting notes, I think there should be no ambiguity. So here, find the time response x of 0 when the input is a unit step. So you have the input here is going to be a unit step, but here you have a mass, you have the spring, and you have the damper. Again, with 0 initial condition. Initial conditions are 0. It is given here initial conditions are 0. If the initial conditions are not 0, then you need to take account for that. And then the parameters are given. The value of the parameters, k over m is equal to 2, c over m equal to 3. So we want to obtain the time response of this. Anytime you see a mass, anytime you see a spring, there is a possibility of oscillation there, depending on the ratio of k over m and c over m. So we don't know yet what's going to happen, so we are going to solve that. We are going to solve this using the Laplace transformation technique. So our first task is to obtain the mathematical model, and then take the Laplace transformation, solve for the output, take the inverse Laplace, and you will get the time response. Okay, so my life is a lot easier now. Everything is there. I don't have to write anything on the board. I can So I can grumble all I like. I'm a grumpy old man by the day. Okay. From example 1, we already have this mathematical model. I'm not going to repeat again how are we going to get this mathematical model. So it's going to be a second order. Why is it second order? Because we have mass. So the second order here comes from mass time acceleration. The first derivative comes from the damping, and we have a spring. So a second order differential equation. But the parameters are given. C rho over m is equal to 3, k rho over m is equal to 2, and now you can substitute C rho over m equal 3, k rho over m equal to 2, and then take the Laplace transform of that with initial conditions equal to 0, and then you get this Laplace, you get this equation in terms of Laplace variable. Again, the capital XO represent the Laplace variable of XO, the capital XI represent the Laplace variable of XI. And then you can solve for the transfer function. This is what we call the transfer function. Is the ratio of the output over the input when the initial conditions are 0. So we get the transfer function. So this is the transfer function. And then we want to solve for the output. We must know what the input variable is. In this case, we are given the input variable is equal to the step input. Therefore, when you take the Laplace transformation of step input, you get 1 over s, and then you can solve for the output variable. Okay. Once you put the input in, and then you can solve now for the output variable. So you put xi is equal to 1 over s. Now this is the expression for the output variable in terms of Laplace domain. Capital XO represent the Laplace variable of XO. And then you need to take the inverse Laplace of this using the table. There's a limited elements in the table. There is no expression in the table equal to this somewhat complex quotient. So somehow you need to turn this ratio into elements that is already available in the table. So you need to form what we call a partial fraction. I think you have learned partial fraction in your math class. See, it is easy being a lecturer. All you have to do is push back everything to the previous lecturers. You have already learned this in dynamics. You have already learned this in mathematics. I'm expecting you to know this. See how easy it is to be a lecturer. You might want to be a lecturer one day. It's easy for me. Yeah, you have learned this partial fraction in your math class. There's no problem. But anyway, I'm going to refresh your memory anyway. Okay, so we are going to decompose this expression into partial fraction. See, when you have 3 terms in the denominator, you're going to have 3 fractions. So the term, the factor in the denominator is s, 1 plus s, and no, s plus 1 and s plus 2. Therefore, you're going to have 3 fractions. A over s, which is s is the first factor, b over the second factor, which is s plus 1, and c is the third factor divided by the third factor, s over 2. So your task is to determine what is the value of a, b, and c. All you have to do is just expand that. You multiply. So the original quotient here is going to be equal to this new partial fraction format. Just multiply everything by the denominator. See, the denominator is s plus 1, s plus 2. Multiply everything by the denominator. So you get just, on the left-hand side, you get this 3s over 2, which is just the numerator. And then every term here multiply by every partial fraction here, you must multiply by the denominator. Then the first term here multiply by s plus 1, s plus 2. So you have this a s squared 3as 2a. That is from the first term. And you repeat that for the second term, and you get the b. And then you repeat that for the third term, you get the c, the c coefficient. And then you need to solve for a, b, and c. You just compare the coefficient of the polynomial. On the left-hand side here, you only have s to the power of 1, so you don't have s to the power of 2. Therefore, the coefficient for s to the power of 2 is just equal to 0. So basically, a plus, no, wait a minute. Okay, 2a plus 2. You look at the constant coefficient here. Constant coefficient here, you have 2, so equal to a. The rest here, you have s or s squared. The only constant coefficient here is just 2a. Therefore, you compare this constant coefficient to a equal to 2. So you have this 2a is equal to 2, and basically you can straight away solve for a is equal to 1. And then you compare the coefficient of s. So 3a plus 2b plus c, 3a plus 2b plus c equal to the coefficient of s on the left-hand side is equal to 3. The coefficient of s squared is equal to 0. So a plus b plus c is equal to 0. So this is the coefficient of s squared, coefficient of s, and this is the constant coefficient. And then you can solve this for a, b, and c. Once you get a, b, and c, then you can now substitute in that fraction there. 1 over s, a is equal to 1, b is equal to 1, c is equal to -2. And now you can look in the table of Laplace transformation. You can simply take the inverse Laplace, because now each of the fraction now is available in the table. Take the inverse Laplace of that. The inverse Laplace of 1 over s is just 1. The inverse Laplace of 1 over s plus 1 is e raised to the power of -t. The inverse Laplace of this is -2 is the coefficient multiplied by e raised to the power of the roots. The roots here is -2, so e raised to the power of -2t. And then if you can draw this response with respect to time, and you get some the response is something like exponential increase of a function, and then you have your transient part, and then you're going to have your your steady state part. Okay, so do you have any question? Do we need to draw the graph in this equation? No, this is a free country. You can do anything you like. You don't have to do anything. Even the test for this class is optional. No, I'm just kidding. Sorry about that. Depending on the question. If the question asks you to draw the response, then you need to draw this graph. If the question just wants you to obtain the mathematical solution of that, then you don't have to draw. So, and then why do I draw this? Why do I draw this response? Because I want to show you there is a transient part, there is a steady state part. What do we mean by transient part? What do we mean by steady state part? In the test, if the question asks you draw the output or sketch the output with respect to time, then you need to draw this graph. If not, then if you just give this mathematical expression, that will be sufficient. Do you have any other question? No, no question. Sometimes we wish that, okay, Do you have a magic whiteboard at home? We miss it. No, I don't have my magic whiteboard at home. My magic whiteboard is in the office. Hopefully that I can get back to office after 14th of November. I miss my magic whiteboard as well. All right, so do you have any other question? Sometimes we wish that we have a simpler method of determining A, B, and C. Do you wish that we have a simpler method of determining A, B, and C? Anybody? Do you wish that you have a simpler method? Yes. Okay, your wish is granted. I'm granting your wish. Yes, there is. There is a simpler way of determining A, B, and C rather than to solve this simultaneous equation comparing the coefficient of the polynomial. We are going to learn that next week. There is a simpler way of that we can determine A, B, and C. It is called the residue method. Sometimes it is also called the what? I always call it the residue, the remainder method. So we are going to learn that next week. So that is the end of our class today. So I'm going to end my presentation here. I'll see you again next week. And don't forget to start working on your assignment. By the way, that assignment, I extract the assignment from previous question from the previous final exam question. So your assignment there, I extract from previous past year final exam. So if you can do that, if you can solve that assignment, you are in a good shape. Okay, so I'll see you again next week.